Hello and welcome everybody to the lecture series on computer graphics, and today we are going to discuss about projective transformations and 3D viewing pipeline. So, essentially we are going to discuss about 3D viewing, and in the last few lectures we had basically discussed 3D transformations, and within transformations the last few part of the material on 3D transformations was basically on projective transformations. So, as a continuity we continue into with the 3D viewing pipeline and projection transformations, and that is the main subject of the lecture today, which is essentially the fifth part of the lecture series. So, if you look into the flow chart, look into the overall flow chart of the implementation of 3D viewing, you essentially give to the 3D viewing pipeline a set of 3D world coordinate output primitives. On the left hand side you see the input here, 3D world coordinate output primitives, which goes through a set of normalizing transformations, and that is the essential part of the discussion today, which we will see. The main focus of discussion today will be what is it do you mean by normalizing transformations, in why it is essential before you apply what is called as a clipping, that is the second stage, clip against the canonical view volume. Now, these are I will say larger groups of tasks divided into various categories. First is applying normalized transformation, the second is clip against canonical view volume. So, this is a new terminology which we will come across today. So, we will define basically immediately next what is a canonical view volume and how it helps in the 3D viewing and the corresponding where does it occur in the 3D viewing pipeline. So, we need to clip, of course there is a separate section and discussion on clipping on both 2D and 3D clipping algorithms, and when we discuss that it will be clear how to clip against a 2D enclosed shape or a 3D volume. So, for the time being we assume that there is a clipping algorithm which clips against a canonical view volume, and after that we project onto projection plane. This essentially we have discussed earlier, and the part of 3D transformations I have discussed in detail about projective transformations, and we also know the general formulation about projective transformations only. So, the third task is known, and the last part is a simple transformation into viewport. We will define what is a viewport also. We have in fact seen this, and we will see again what is a viewport in a 2D device coordinates for display, and the 2D device coordinates are generated. So, input is 3D world coordinate output primitives in terms of lines, polygons, circle, text in 3D, and essentially those 3D coordinates are transformed into 2D device coordinates, which must be given to the electron gun to fire the corresponding pixels on the screen. But in between there are four subcategories, and essentially in this in the four subcategories, number one is, as you see again on the screen, applying normalized transformation, second is clip against canonical view volume, third is projection onto the plane, and the fourth of course is the transform into viewport. Out of them we have discussed the third category, that is projection onto the plane. Of course, we will see the formulation once again, the formula of the general projection transformation matrix, but before that we need to do clipping. So, we will understand what is canonical view volume, and before that we will essentially, the major part of the discussion in this particular lecture is applying normalizing transformations. Okay. So, we will see first what is a canonical view volume. Well, there are two types of canonical view volumes which are used in projection geometry in terms of 3D viewing. One of them is the parallel projection canonical view volume, and the other of course should be perspective projection canonical view volume. So, the canonical view volume for parallel projection is defined by the set of 6 planes. It's essentially, you can visualize this to be a rectangular parallelepiped, almost a square, not exactly, a rectangular parallelepiped, where along the x and y dimensions or the x and y axis, the difference between the two binding planes are at plus and minus 1 respectively. So, along an x and y the size is 2, and along z axis the size is 1, because it starts from z equal to 0 and ends at z equal to minus 1. So, along the viewing axis, which is minus z axis, the canonical view volume is bounded by an FP or BP, which means basically the front plane and the back plane, or also called the front clipping plane and the back clipping plane respectively. FP and BP is what we use, and FP is nothing but the XY plane z equal to 0 and the back plane is nothing but z equal to -1. So, both planes are parallel to the xy plane, and that is the front plane and the back plane defined by z equal to 0 or z equal to -1 as given the right hand side of the equations, and the rest x equal to -1, y equal to -1, x equal to 1, y equal to 1. So, basically if you think of a square or rectangular parallelepiped, you need 6 surfaces to bind a volume, and those the corresponding equations of those 6 planes are given here by these 6 very simple equations as given on the top. And this is how the side view of the canonical view volume for parallel projection is given. Let us look now into how this canonical view volume takes a shape for a perspective projection. Correct. Now, you can see there is a relation between the perspective geometry and perspective projection canonical view volume, as well as the parallel projection and the parallel projection canonical view volume. Remember, in parallel projection we have the rays which are parallel and hitting the corresponding projection plane, and in the case of perspective the rays will focus or meet at a particular point. So, that is why you have a tapering effect of the canonical view volume for perspective projections. We still have 6 planes which define them as x equal to z, x equals -z. So, they are inclined planes symmetrically located with respect to the origin or the -z axis, and y equals z, y equals -z, and z. The front plane and the back plane is defined by a z equals -1, which is the back plane as given in the figure here. You see a -1, which is this point basically. The z equal to -1 equation gives this plane, and the z equal to -z mean gives the front plane. You can actually put this z mean equal to 0 if you like, but typically it is a non-zero value which is less than unity. So, that is the front plane and the back plane being talked about for perspective projection. To look into a comparison, I will roll back the slide and you can have a look into the comparative figures. This is the canonical view volume for parallel projection, and this is the canonical view volume for perspective projection. You see a sort of a rectangular parallelepiped structure because rays are parallel here and the rays taper off and meet at a focal point. So, that is why you have a sort of a pyramidal structure, I should say, for a canonical view volume for perspective projection. We are only seeing the side view. You have to visualize the 6 planes which bind this particular view volume. So, that is the idea, and we will see later on, not in this lecture, when we discuss about clipping, how to clip certain line segments or basically line segments or even planes with respect to this canonical volume. Later on when we discuss in clipping in a different section, but we move on because we have to now actually capture this entire world into a canonical view volume before we project it into the projection plane in the third step. So, we will look back into this flow chart, and typically this is the diagrams for an arbitrary 3D view. I did cover this under projective 3D transformations, under projective geometry, and I hope you remember all these terminologies which I will repeat once again. The term VP means the view plane, VUP means the view up vector, which is given by this yellow line or arrow representing the view up vector. CW is the center of the window or the viewport, which is defined by the coordinates u min, v min to a maximum u max, v max respectively. This gray color, the light blue color outside is the view plane. VRP, okay, is the view reference point, VRP, which may not be the center of the window. VRP is the reference coordinate on this on the projection plane, with respect to which you have the u and the v axis, the 2D coordinates axis on the viewport or the projection plane defined, and of course the n or the VPN, which is nothing but the surface normal to the projection plane. We have a VPN along the normal n to the surface, and so I hope you remember and recollect these terminologies, based on which we also define the projection geometry and the projective equations for both perspective and on orthographic or parallel projections. Okay. We look into the next diagram. This is also a diagram for perspective projection geometry, and the VP and the VPN are same, that is the view plane and the view plane normal. We have the center of window, we have a view reference point. In addition, we have a center of projection or perspective reference projection respectively, a center of projection basically, or PRP as it is called, projective reference point. PRP is projective reference point, or COP is talked about where the rays meet, and basically for the parallel projection the COP goes to infinity, and that is why the we can have a PRP defined even for the perspective geometry, but the COP basically goes to infinity because the rays have to be parallel to the projection plane. In this case, for the perspective case, they meet at the center. So, I hope you remember these particular these two diagrams, which we also covered in projective geometry earlier. Typically, in a general framework of computer graphics, you need to specify an arbitrary 3D view. Of course, you must ensure that when we specify an arbitrary 3D view, the camera is looking towards the objects, and the objects are within the view zone of the camera and things like that. But let us take a typical example or a few examples of the viewing parameters, just a few set of example values to give you a rough idea about how to set these parameters, and then of course we will see how these parameters are used for normalizing transformations and also for projection geometry. The viewing parameters used are VRP, which is view reference point, VPN, view plane normal, view of vector, VRP, projective reference point, or COP or PRP, and the corresponding window coordinates of the viewport, the view reference coordinates. So, in bracket it means these VRP, VPN, VUP and PRP are in the first three are in world coordinates, WC, VRC is view reference coordinates, projection type could be perspective or parallel, and you can also have the front plane and the back plane coordinates defined. It is optional with respect to VRC, and the values are given for the set 1. You may not define them since it is optional. Set 2 and set 3 does not contain the values for the front clipping plane and the back clipping plane with respect to the view reference coordinate systems. So, if you look into set 1, these are typical example values which you can specify for the arbitrary 3D view, and you can make a function call with this set of parameters, and you will set up a specify arbitrary 3D view for the object for you. Okay, so that's just a typical example. When you use the graphical software and the corresponding fixed standards, you have to use these sort of conventions, and these are just example values which you can use. Okay. Well, we go into the steps for implementing normalizing transformation matrix in the case of parallel projection first, and then we will look into the perspective projection, and the set of steps are defined in the slide. The first step is you need to transform the VRP or the view reference point to the origin. Okay, translate the VRP to the origin. So, you need to have a translation matrix first, and then you have a rotation matrix which helps you to rotate the view reference coordinates such that the n axis or the VPN or the view plane normal axis here aligns with the z axis of the world coordinate system, and in turn also the u with the x and the v with the y. So, u aligns with x, v with y, and the VPN aligns with the z. I hope you remember the VPN which we just talked about, and what this means also figuratively will describe as to what you mean by translating and at least rotating this, because the second step of rotation is the most crucial step in this process of implementation, and the rest are very easy steps, but I will complete this sequence of steps. So, the third step is basically shear, which is not necessary for pure orthographic projection. Generally necessary for parallel. We know orthographic is a special case of parallel projection, and in the case of non-orthographic parallel, where the direction of projection or DOP is not parallel to the z axis, we need to make it parallel to the z axis before you actually project it. So, you may need a shear in case of parallel projection which is non-orthographic in nature. So, that is the third step, but remember it is non-optional, but we will have a shear matrix as the third step. In the fourth step, you have the translate and scale into parallel projection canonical view volume. We know the planes which define the canonical view volume, and you need to provide a translation and scale to adjust your view volume to the canonical view volume. This is also necessary before in the view pipeline, before you actually use the projection matrix, and in fact before you use the clipping itself, and this is the form. So, these are the sequence of steps, and you see if there are 5 different steps, it results in a composite matrix with 5 different matrix multiplication in the particular order, and since the first step is the translate VRP to the origin, so that is the T with a minus VRP parameter. Then you have the R, which we are going to discuss in great detail today, and then SH matrix parallel means the shear in case of parallel projection, and then T and S successively for parallel projection respectively. This S and T correspond to the last step, 4th and 5th respectively, which says translate and scale into parallel projection canonical view volume. So this is the sequence of operations one is to do of the first stage itself of the 3D weaving pipeline. If you remember the flow diagram which we talked about at the beginning of the lecture today, there were 4 stages. The first stage was the normalizing transformation, second was clipping, third was projection, and fourth was a simple 2D in the viewport. Okay. So the first one is what we are discussing now, and these are the 5 steps of the first stage itself, the normalizing transformation. Okay. So you need to normalize such that the entire world, what this stage does is the entire world is brought into the canonical view volume so that you can apply clipping easily, and you can also apply the perspective projection transformation matrix. So perspective projection transform matrix, although we know the generalized form, before you can apply, there are in fact 2 sub stages. Okay, prior to that, one is clipping, which we will of course discuss later on. So don't worry about it for the time being. I keep repeating, don't worry about clipping. We will do that with respect to the canonical view volume when we discuss exclusively clipping in 2D and 3D. So we'll discuss mainly the first stage, which is the normalizing transform, and that has 5 stages as given here, and the composition matrix N par. N par is nothing but the overall normalizing transformation matrix for parallel projections, and I repeat, it has 5, it is composed of a sequence of 5 different operations or 5 transformations. First translate T, then rotate R, then shear SH, then a translation T, and again a scaling S bar. Out of this, the most significant translations will be very easy, as you can visualize. We will first discuss R and then of course spend a little bit of time about the shear. So rotation is the one which is very crucial, and we will see why. Okay. So the step 2 of normalizing transformation, I repeat that state again, is you have to rotate the view reference coordinate system. The view reference coordinate system, which is defined with respect to the viewport and the camera and things like that. So the camera will have its own U, V and the N axis. You have to rotate that, translate of course the VRP to the origin, and then rotate in such a manner such that it gets aligned with the world coordinates, which has the, that's that the VPN or the N axis, the view plane normal, aligns with the Z axis of the world system, and the U and the V also aligns with the X and Y axis respectively. So this is the most difficult step 2, the most difficult task in normalized transformations. And just to give an example, what I mean by this, let us see this XYZ or XYZ is the world coordinate system. That means you have defined your originally the world coordinate system with respect to this XYZ as origin, and however the camera is in such a position that it may not be at the origin, it may not be at the origin of this system, it could be at arbitrary some position looking down some other direction, and there is where you have the N, U and the V axis which define the 3D coordinate system for the camera, let us say, because through the camera you are basically looking into the visual, the virtual world which gives the visualization. Okay, and the camera will have its own view plane normal of the N axis, it will have its own X and Y which we call it as U and V, and this diagram we already know where is the view plane, what is the view of vector, what is the VPN, center of the window CW, view reference point and all that. So the first stage is to basically take this diagram or the with respect to the camera or the view system, and first give a translation so that the VRP goes to the origin, and then give a composite rotation such that the VPN has to align with Z, U with X and V with Y. I repeat again, first the VRP has to be taken to the origin, here it will go, I repeat VRP is here, it has to go to the origin at this point, then the VPN or the N axis should align with the Z axis here. Okay, I hope you can see the cursor, then the U axis should align with X and the V with Y. Okay, so these 3 must simultaneously happen together with a composite rotational 3-dimensional rotation matrix, 3-dimensional composite rotation must take place to have this alignment done. So this is the most crucial stage or step in normalizing transformations, and this requires a sequence of operations. Now how to get this R? How to get this R? Yes, you will probably start thinking about various types of 3D rotations and transformations which take place, but we dig into a little bit of depth of mathematics here to easily understand about 3D rotations, get some principles out of the matrix property of rotation and see how easily we can formulate this R. Okay? And then we go to the next slide. So, we are essentially now under the first category or first stage of normalizing transformation. Within the 5 steps of the first stage, we are in the second step. Okay. First stage of the 4 stages is normalizing transformation. In that first stage, we have 5 steps, and in that 5 step, first is translation, second is rotation. So, we are talking of step 2, that is what is given in the slide. So, we are looking for expressions for step 2 which must be derived, that is what we are looking at, and we implement that using the concept of what we call as combined transformation or rotation. Let us take a rotation matrix Rx. This rotation matrix, you know what does it do? It takes a point in 3D space and rotates about the x axis. Okay. So, the x axis coordinates of that point will not be disturbed. Assume that x axis is pointing towards you. Okay. You rotate it about the x axis. So, the x axis coordinates of that point does not get disturbed, but what are the 2 other coordinates which change? Y and z. Y and z are the 2 coordinates which change, and that is why you see the parameters cos alpha, sin alpha. Of course, we are talking about looking into the axis and counterclockwise rotation, positive alpha, the second and third axis will have the cosine alpha, sin alpha terms causing the change in the y and z coordinates. X axis will not change. Okay. So, let us try to visualize this from a slightly different angle, this rotation. I make here a statement and we will validate that with a figure and illustration later on, that if you take the rows of this matrix Rx as unit vectors, that is what is written. If rows are unit vectors, you remember it is very easy to see here that due to the orthogonal property of this Rx matrix, the rows and the columns are unit vectors. So, take the rows as unit vectors, and when these unit vectors are rotated by this rotation matrix Rx, they will align with the y and z axis respectively. Well, it is difficult to straight away visualize when I am making this statement, but I will explain that soon with the help of a figure, but just note down now that the rows are unit vectors. If you take the rows, I will take these rows of this matrix, each row is a unit vector, you can verify that. Take the first 3 terms of each row, do not have to take the 4th term, because the 4th term on the 4 by 4 matrix is coming due to the homogeneous coordinate system. So, take just the top left 3 by 3 submatrix and take the 3 elements each row, because 3-dimensional vector we are talking about. So, each of these rows are unit vectors, and these unit vectors, I say that when they are rotated by Rx, I did say that the x coordinate does not change. So, 1 0 0, the first row vector remains 1 0 0 itself, but the next 2 row vectors, which are again unit vectors, they will get aligned with y and z axis respectively. It is a very nice phenomena which we will discover now with an example, but before that there is another complementary or similar concept where I say, what the column vectors? If I say if the rows are unit vectors and they are rotated and will align with y and z respectively, then the second point says that if I take unit vectors along the principal axis, if I take unit vectors along the principal axis of the coordinate system and those unit vectors are rotated by Rx, they form the corresponding column vectors as given here in this matrix. So, if you take the column vectors 1 0 0, 0 cos alpha sin alpha, 0 minus alpha cos alpha, you can form these vectors by taking unit vectors along the principal axis and then rotating by Rx. Take the principal axis vectors, unit vectors, rotate them, you get the column vectors. On the other case, if you take the row vectors and then rotate by Rx, they will get aligned with the principal axis y and z. Very interesting phenomena here, and we will see with an example figure as to how this happens. Again, I repeat, this is again the row matrix Rx as given on the top, and what are those row vectors? I have given here. The row vectors on the first row I get a 1 0 0, that is the first row vector 1 0 0 as given here. The second row vector, take the first 3 terms, upper left submatrix 0 cos alpha minus sin alpha is the second row. Okay, and the third row is 0 sin alpha cos alpha, 0 sin alpha cos alpha. So, these are the 3 row vectors in 3D. How will these row vectors look like? Okay, let us take a 3-dimensional coordinate system as given this figure on the left hand side of the slide with you, and the x axis is not shown because it is coming out from the slide and pointing towards you. Okay. You can take a right hand coordinate system and say assume x to be pointing towards you. So, I have not drawn that because you are essentially rotating around the x axis. So, it will rotate about this origin in 2D, x axis is pointing towards you, to the right you have y and the vertical one is z. So, look back into the figure, you will find x axis pointing towards you, y to the right and z axis vertically upwards. So, now look back into the row vectors which I have just written. Look at the row vectors and try to map it onto the system. You will find that the 1 0 0 vector is nothing but it is along the x axis pointing towards you. Anyway, since you are rotating by r x, it does not matter, 1 0 0 nothing will happen. What about the second vector? 0 cos alpha minus sin alpha. You look at this, I have labeled with the same color as the row vector in text. This is the corresponding yellow vector which is giving the second vector, because if you look, this is the angle alpha, then the x coordinate, and if it is a unit vector, then the y coordinate will be cos alpha and the z coordinate of that vector will be sin alpha in the negative direction, hence you have minus sin alpha. Correct. So, that is the second vector. The third vector also, corresponding color I have used, it is also sin alpha along the y and z alpha along the z axis. So, these are the two vectors which are the second and the third row vectors of the transformation matrix R x. Now, what will happen if I take these two vectors and give it a counterclockwise positive rotation alpha? You can visualize what will happen if I give it a rotation by m naught alpha. What will happen? The corresponding row vectors will automatically get aligned with the y and z axis. Very interesting, isn't it? You have them bent and they will turn and then they will get aligned with the y and z axis respectively. This was being talked about as the point in the previous slide. I will show that point once again, where you take the row vectors as given the transformation matrix, and those row vectors, when given a corresponding rotation by the same matrix, they will get aligned with y and z. Now, what with the column vectors? I can use the same diagram and visualize the column vectors. Now, for the column vectors, what you assume is, let us take, you take a column vector, you take a unit vector along y and z respectively and give it a negative rotation. That means, now clockwise looking into this figure, negative rotation r x of minus alpha in this case, what will typically happen is you will get the corresponding column vectors as 1 0 0 0 cos alpha minus alpha. Remember, r x of minus alpha. So, what will happen is, in this matrix the sin alpha here will change sign to minus, and in the third column the minus will become plus. Correct. So, that is what is happening here, that the reverse could also take place. You could have given a positive alpha and seen what could have been the result, but in this case a negative alpha with the same figure, I can show you that if you take unit vectors along y and z, give it a clockwise rotation negative alpha, you will get the column vectors exactly as given by the transformation matrix. So, this is an interesting phenomena which we will use to derive the general transformation matrix, in which you have an arbitrary coordinate system and you need to give a composite rotation to get it all aligned with another coordinate system respectively. Okay. I will roll back those 2 points once again. You see here, these are the 2 points, okay, where I say, I repeat again, if rows are unit vectors and then they are rotated by a rotation matrix R x, remember, then they will get aligned with the y and z axis respectively. We have seen that these rows are the unit vectors obtained itself from the R x, and the next point is, when unit vectors along the principal axis are rotated by the same transformation matrix R x, they form the corresponding column vectors of R x. So, that is a very interesting phenomena, and we have seen that with the help of this example. You can copy this figure and the corresponding row vectors, column vectors, and keep checking it yourself with both positive alpha and minus alpha rotation. Of course, you can use R x, R y, or R z, you will also get the same effect. Okay. So, keeping this concept in mind, that the row vectors can be rotated and formed, and they form the vectors as given in the rotation matrix, and the column vectors you take which are in fact the row vectors get aligned with the y and z, and in the case of columns you take unit vectors along y and z, and what happens is they form the vectors as given by the R x. So, if that is true, and this is possible to use this concept and this idea because of the property of the orthogonality of the matrix, because unless the matrix would have been orthogonal, you would not have had the rows and the columns giving you unit vectors. That is number 1. Okay. And so, if that is the case, I make a step jump and come to a general scenario of a combined rotations, where I use this property based on the orthogonality of the R matrix, where I say that if this is a scenario of 3 different vectors, I will say on a system x, y, z, I have a vector, the yellow vector p1, p3, the whitish vector given by the white arrow p1, p2, and the dashed vector in blue color p1, pn. So, there are 3 vectors, and in this, within these 3 vectors, I must tell you that the p1 and pn is nothing but a vector which is normal to the surface obtained by p1, p2, p3. So, actually what it means is you can take a cross product of the 2 vectors p1, p2 and p1, p3, that will give you the normal vector pn, that is the relation. So, basically pn, p1, pn is normal to both p1, p2 as well as p1, p3, whereas p1, p3 and p1, p2 may not be orthogonal to each other or perpendicular to each other. So, Pn can be visualized again, as I say, as a normal to a surface formed by P1, P3 and P1, P2 vectors. But what I essentially want to do is, I want to get this set of vectors aligned with the, at least 2 of them I can get aligned with 2 of the other axes in x, y, z, because I have perpendicularity with respect to Pn and P2. P1, Pn is perpendicular to the P1, P2. So, before transformation, if this was the scenario, I would like to give this set of 3 vectors a combined transformation where these 3, let us say, get aligned with the homogeneous. If this is the x, y, z, and I have this p1, p3, p2, pn vectors, and I will give it a combined transformation to get itself aligned with x, y, z, and now we go back into the slide, and I want to give it a combined transformation. After transformation, I want the following to take place. The p1, p2 vector before transformation was given in the previous figure, here in the same slide, gets aligned with the z axis, and the corresponding normal to that, the p1, pn, the blue colored dashed one, gets aligned with the x axis, and of course, p1, p3 also takes its own place somewhere, because it has to be perpendicular also to the P1, Pn. So, basically this P1, P2, P3 vectors will actually, these 2 vectors will lie in the plane yz plane. That is bound to happen with this set of transformation if I take place. So, if you remember the previous 2 concepts which we talked about in orthogonal matrix in terms of rows and columns, which one was the property which, given a rotation, arbitrary vectors or some vectors get aligned with the coordinate axis x, y, z? We have to deal with rows, because if you take the rows as unit vectors of the transformation matrix and you give it a transformation, they in fact get aligned with the corresponding principal axis. Okay. So, that relation we will keep in mind, and the corresponding transformation rows or columns of the transformation matrix can now be in fact defined or obtained directly from these vectors. Correct. If you just expand this concept from 2D, which was a rotation around the x axis, to a general scenario, just a step more, of course, you can derive analytical expressions and check this also, but if you just draw an analogy to a general 3-dimensional scenario, what will happen is now that you can derive this transformation matrix from the vectors directly. That is the advantage. Okay. Remember the previous examples we have taken with rows and columns with the transformation matrix Rx. Keep that in mind, and we will derive now. Okay. So, let the effective rotation matrix be a combination of 3 rows as given by this, where I will say the first row corresponds to something in x as R1x, R2x, R3x respectively, second with respect to similarly with y, and similarly the third row is with respect to this, and this is the effective rotation matrix which will cause that transformation to take place. And if that is so, this rotation matrix, what it is supposed to do before transformation? That's P1, P3, P1, P2, P1, Pn vectors will be transformed, 3 vectors will be transformed in such a manner that the P1, P2, the purple color vector will get aligned with the z axis, the whitish dashed vector P1, Pn will align with the x axis, and of course, the P3 vector will also lie somewhere in the yz plane. To implement this concept, we will look back into the equations, and here the corresponding form of the coefficients of this combined or effective rotation matrix is given, and we will start with the bottom row, last row of that matrix, where I define RZ to be a vector of the last 3 coefficients of the last row elements of the matrix, given by what? It is nothing but the unit vector along P1, P2. So, if I put the elements of the last row equal to the unit vector along P1, P2, that will help me to get this vector aligned with the z axis after transformations. Similarly, next what I have to do? I have to take this P1, Pn vector and align with the x axis. So, my first row, which consists of the elements R1x, R2x and R3x respectively, which is given by the vector Rx, is nothing but the vector P1 Pn. And what is P1 Pn vector? It is nothing but a cross product of P1 P2 and P1 P3. Unit vector along P1 and Pn can be obtained by the cross product of P1 P2 and P1 P3. So, that is the unit vector which is given by P1 P2 cross P1 P3 cross product divided by the norm, correspondingly will give the unit vector along P1 Pn, and that gives the elements R1x, R2x, R3x respectively. So, the top row and the last row elements or coefficients of the matrix are already obtained. You need the middle row, which is nothing but the R1y, R2y, R3y respectively. They are nothing but, easily you can visualize that they have to be nothing but a cross product of the 2 vectors P1 P2 and P1 Pn are nothing but basically Rz cross Rx. That will give you nothing but the vector which will align automatically with the y axis, because after you have aligned P1 P2 with z, P1 Pn with x, automatically the cross product of these two will get aligned with the y axis respectively. So, the cross product of Rz and Rx will be the elements of the y axis. So, this is the philosophy or concept by which you come up with an effective rotation matrix by which any arbitrary 3-dimensional coordinate system can get aligned with another coordinate system respectively. Of course, we are talking of Cartesian coordinate system x, y, z and n, u, v, let us say, and you want to put this here or you want to put that here, sort of a thing. You can do that very simply if you know the corresponding vectors, unit vectors of the other axis with respect to the one which you are mapping onto or aligning it with, and if you know these vectors with respect to this coordinate system, let us say the source and the target, then you just form the transformation matrix with the help of these vectors, put the coefficients as these unit vectors, apply that, and the system gets aligned. So, that is the basic philosophy of the rotation matrix, which is essential for implementing step 2 of the transformation or normalized transformation. Okay, so, understand the theory now, and I repeat this figure once again. This is essentially showing the figure in which the rotation matrix of steps 2 has to be formulated in a manner in which we illustrated with respect to this figure, where I made P1, P2 align with the z axis and the P1, Pn align with the x axis respectively. And if I can do that, similarly I can do it for my normalizing transformation, where I need to take the VRC or the view reference coordinate system and align it with the world coordinate system, and I will have the similar form of the rotation matrix. And remember, I repeat the step 2. This is what we have been discussing, how to implement this step 2 in normalizing transformations, and it says that you rotate the VRC such the view plane normal or the n axis aligns with the z axis, and also you make u align with x and v align with y axis respectively. Okay, so that was your world coordinate system x, y, z, and you had to align this, correct? This figure comes again. I repeat this because this is essentially what we were planning to do and we have to do, and we have understood the basis theory of how to do that. How to do that? Now you need to just align Vpn with the z axis, u with the x axis, v with the y axis. This was our original problem, and we know to solve it. We know to solve it because if you know the vectors Vpn, u and v with respect to the world coordinate system x, y, z, you can form your rotation matrix with the help of these vectors, and that is the rotation matrix which will help you to get this system aligned with the world coordinate system. So, let us look at this form. Okay, that is simply like the one we did. Take the z axis, the last row of coefficients, the Rz, which is nothing but the view plane normal. So, take the unit vector along the view plane normal, that will give the last row of the transformation matrix for rotation, in the transformation matrix, the last row in the z, and the x will also be obtained by a cross product of the v of vector and Rz. Let us go back to the figure to understand the significance of Rx here. It is a cross product of v of vector and the and the view plane normal. If you take the cross product of view up vector is nothing but points which is the up vector, it is lying in the NV axis, and the cross product of the view up vector with the VPN will actually give you nothing but it will actually give you the U axis. So, the specification of view up vector and VPN itself, these two vectors sufficient to tell you where is your U axis, and a combination of u and v of vector will tell you or the VPN and the u will tell you where is your v. But to get u given VUP and given VPN, I repeat, given VUP or the view of vector or given view plane normal or the VPN, the cross product of these two will give you the v axis. So, that is the concept of taking the cross product of view plane normal, which is nothing but RZ, and VUP gives the elements of x, and of course, the elements of y, which is the second row, can be obtained easily by the cross product of RZ and Rx. So, these are the expressions, these are the equations which will help you to get the expressions for the combined transformation or the rotation matrix. Okay. So, that is the step 2. So, the step 2 coefficients can be obtained by Rx, Ry, Rz respectively individual rows, and they are computed, nothing is required except you require the view plane normal and view up vector. Once VPN and VUP are given, you can actually obtain the Rx, Ry, Rz elements required for the rotation matrix, which is the step 2, and that is the step 2. Remember, there were 5 different transformation matrix required for the overall combined normalized transformation matrix for parallel projection. I have put in bracket WCSVB to be projected to PPCVB. I will explain what these terminologies mean. Well, WCSVB you can expand to world coordinate system view volume. World coordinate system view volume has to be transformed to a parallel projection canonical view volume, PPCVB. World coordinate system view volume to a parallel projection canonical view volume. Okay, that is what we have been discussing as the overall combined transformation matrix, and it consists of 5 different transformation matrices. First, you remember the steps: translation, rotation, shear, translation, scale again, and after the translation with respect to minus VRP. So far, in the most part of the talk in the last half an hour or so, I have discussed how to get this R, and the equations to obtain the elements of R are given in the same slide on the top. The third, the last row of R is given by the VPN. VUP multiplied by VPN cross product gives you the first row, the elements of X, and RY can be obtained by the cross product. So, once you get R, the first 2 stages are over. You need to only find out what is, how to get the shear transformation matrix and what should be translation and scale. So, we will discuss in the remaining time these 3 transformation matrix and complete the first stage of the normalizing of the viewing pipeline of the normalizing transform. Okay. So, this was the equation, the combined transformation matrix for parallel projection, which transforms a world coordinate system view volume to a parallel projection canonical view volume WCSVB to a PPCVB is given by these 5 transformation matrices, and we know that how to get R and T. What is the shear matrix? The shear is necessary. If you remember carefully this, when I was discussing these steps, the shear matrix is necessary for a parallel projection which is non-orthographic. Parallel projections could be 2 types. It could be orthographic, non-orthographic as well as axonometric, isometric and all that. What is the difference between orthographic and non-orthographic among the class of parallel projections? Well, in case of parallel projections, there is no doubt that the rays will be all parallel and they will be going towards the direction of projection somewhere, towards infinity. COP, center of projection, it goes to infinity. That is why the rays are all parallel, but there is a direction of projection. That direction of projection may not be normal to the view plane. If it is normal, it gives orthographic. If it is not normal to the view plane, if this is the view plane, then if they are all perpendicular to the view plane, you get perfect orthographic parallel projection. But you can have non-orthographic parallel where the direction, the parallel rays are now not normal to the surface, they just come and hit it in inclined manner. So, that is a case where you need to provide a shear to the view volume now. Otherwise, if it is pure orthographic, rays are anyway parallel or I am sorry, normal to the projection plane, then you do not need to provide this third step or the middle step of shear. And to explain this shear step, I have 2 figures where before, this is the side view of shearing of the view volume. What actually may happen is, as you can see in the left hand side, bottom of the frame, you have a view plane normal and the directional projection is somewhere different. It is not parallel to the view plane normal. This can happen in a parallel projection which is non-orthographic in nature. In case of an orthographic, automatically direction of projection and view plane normal will actually be parallel. You do not need to provide this shear, but here the direction of projection is not aligned with the view plane normal, and you need to provide a shear to this view volume to make that direction of projection align with the view plane normal, and that is given in the side with a side view of the shearing of the view volume. If we can provide it shear, the right hand side figure, this what you can say is this rhombus type of figure basically becomes a perfect rectangle or a square, and that helps to make your directional projection and the view plane normal the same. They are now aligned, and that can be provided by two types of shear along the x and y axis. You need to give the shear, and the shear parameters, the matrix is given here SH par, and it has just two elements here, SHX par and SHY par, and I leave it as an exercise for you. The first exercise in this today's lecture is to obtain this SHX par and SHY par elements of the shear. We have discussed about shear matrix in theory transformation. You should be able to derive that, but the answer is given to you here, where the elements are nothing but the ratio of x to z component of the direction of projection vector. DOP vector is the directional projection vector. So, x component of that divided by z give you the SHX par, and the ratio of y to z gives you the SHY par. Okay? The SHY par is given by DOP y by DOP z respectively. Okay. Well, so we are discussing this stage of overall combined transformation, and there are two stages left. One is scale and another is translation, and I leave it an exercise for you. This last two stages of translation and scale are required because the canonical view volume has to be, the view volume has been transformed after rotation, translation, shear, but it has to be shrunk to the canonical view volume defined by the 6 planes in parallel projection, and to do that before itself scaling you might need to translate it such that the front plane gets aligned with the corresponding xy plane, and the corresponding umax, umin, vmax, vmin had to be aligned. So, you need to do a little bit of translation in 3D to align it perfectly and then give it an overall scale factor. You see that the T is a vector, the T matrix, whereas the S is given as a functional form. These are the 3 diagonal elements of the shear matrix which are given in the last equation, and you provide that scale. You provide that scale to actually fit it and form the canonical view volume in parallel. In the time remaining, we will quickly go through the perspective transformation matrix for normalizing transformation, and the steps are almost similar to case of parallel projection, only now the canonical view volume will have a different shape. It is like a pyramid, unlike in the case of rectangular parallelepiped in the case of a parallel projection. Okay. So, these are the equations, 6 planes we talked about in case of perspective projection. So, it is forming a pyramid. We are having a side view in the xz or yz plane only we are looking. If you look into either xz or yz, you will have this figure. It is like basically a pyramidal structure. Okay. The steps, I will quickly go through the steps. It is almost the same. Translate the VRP to the origin, rotate the VRC. The second step is also the same. You do not need a shear now. Prior to that, you need a translation because there is a center of projection or a perspective reference point or a PRP or a COP which comes. You need to provide a translation first, then you need to provide a shear so that the center line of the view volume becomes the z-axis like the directional projection which you had in the case of parallel projection, and then you of course do a scale. So, the sequence of steps are almost similar, especially the first two, and then of course the last 3 are a little bit jumbled up in the sense that the translation first, then the shear, and then the scale. Okay. This is the scenario of the cross section of the view volume after first 3 transformations. What are the first 3 transformations? Translate with respect to minus VRP, rotate, which we have discussed first, the rotation of the one system to the other, and then of course you translate it to the minus with respect to minus COP or PRP. Then you need to give it a shear, because what may happen after the first 3 stages of translation, rotation, translation is the view volume may, before giving it a scale, it may appear something like this. It may not be perfectly aligned with the z-axis. You need to do this, otherwise the canonical view volume will not come in shape and you cannot apply the projective transformation later on. So, the view volume center line VVCL as given here passes to the center of the window from the origin, and this has to be aligned with respect to the minus z-axis, and that is what is required, and that will be provided to by the SH par matrix which will give you that shear. Okay. So, this is the overall, and just as a comparative study of the overall combined transformation matrices for parallel and perspective, as you can see here, the nature is almost same, specifically the first two transformations T of minus VRP and R are same. Then we have a translation and shear in the case of perspective. In the case of a parallel on the top, you have first shear and then translation. So that is the reverse, and the end anyway we have to have the scaling to scale it to the corresponding canonical view volume. So that is the comparison between the two projection geometries of transformation matrices. And now if you go and look back, we will stop with this today, that we come back to this original viewing pipeline, the implementation of the three viewing pipeline which we started to talk about today. And you remember, I repeat again, we start with 3D world coordinate output primitives, apply a normalized transformation, then clip, then you have to project in the projection plane, and ultimately the 2D transformation to get the 2D device coordinates. So far what we have discussed in the entire lecture today is the first stage only, the applying normalizing transformation, and that to two parts of it. One is the parallel geometry, parallel projection, another is the perspective geometry, and among those there are 5 steps of transformations in the first stage itself of applying the normalized transformation, and among those 5 steps the second step, rotation, was probably the most crucial one. Of course you have to apply the shear and the scale as well. So applying the normalized transformation consists of 5 steps, both in the case of perspective and parallel projection geometries. Then you of course need to provide a clip in the canonical volume, and then we project into projection plane. Now the third stage is the projection plane. This we have studied earlier in the case of 3D-dimensional transformation itself. I will just flash this slide so that you can recollect the general transformation matrix for projection, and once that is done you need just a 2D scaling in terms of the transform into viewport in 2D coordinates for display. And the next slide is the third stage, that is because the second stage of clipping we will discuss when we talk of clipping entirely in 2D and 3D. So we know now the first stage. The second stage of clipping will come in due course of time when we talk of clipping. The third stage in fact we have already discussed under 3D-dimensional transformations, and this was the generalized formula. If you remember, the generalized formula for perspective projection matrix was given as this. This we derived in the previous lecture under 3D-dimensional transformations. Under 3D-dimensional transformations we discussed a lot about projection geometry, parallel axonometric, trigonometric, 1 point, 2 point, 3 point perspective geometry, and also transformation matrix in the case of perspective geometry. And also this is a generalized projection matrix, both applicable for perspective and parallel. And if you recollect back into the notes which you have taken from the slide, you can put special cases of the values of dx, dy, dz, direction of projection, and q, which will take the COP to either infinity or in a finite distance will give you projections of perspective or parallel or orthographic. Okay. So with this we stop today, and we continue with the 3D viewing pipeline in the next lecture. This is the perspective projection matrix which we use as the third stage of the viewing pipeline. I go back and we stop with this same slide which we were talking, and we started with this slide where we have discussed extensively about applying normalized transformation, and we have discussed also seen the expression of the third stage which is projected onto projection plane. We will probably not discuss canonical view volume clipping now. A little bit of transform into viewport we will discuss, but in the next lecture we will start from this and we will see the viewing pipeline broken up into several stages, where we start from object model coordinate system, pass through world coordinate system, go into the I-space or image coordinates, and then to device coordinates. Entirely a sequence of transformations which take your object somewhere in space, the camera is somewhere here, the object is somewhere here, model, and the sequence of transformations which will slowly take all these into the device coordinates in the screen on the TV or the projection system which you see. Okay. So we stop here with the first lecture on 3D viewing, and we will continue this with the 3D viewing pipeline with the different matrices revisited again and the different stages, and how to get the 2D device coordinates and viewport. Thank you.